welcome to my presentation on network-based multi-scale hybrid data-driven analytics. My name is Reza Said Kandezi from School of Electrical and Computer Engineering, University of Oklahoma. To begin, let's discuss the importance of understanding of the system dynamics. Understanding system dynamics require a multi-scale analytical framework, crucial to the case of heterogeneity due to the intermittent nature and the rapid response of our integrated multi-scale resources, resulting that this result in uncertainties and fluctuation that leads to unpredictable disturbances or cascade failures. Those uncertainties caused by the multi-scale components translate normally to modulational uncertainty, or even in a hard situation, modulational instability, and some complex interaction between the component, which is, as we discussed, would emerge a frequent disturbance or cascade failures. Traditional analytic method falls short in accurately modeling these behavior and predicting the dynamical behavior, especially during a transient state, due to the system level, or as we call it, second order nonlinearity in the system. The aim is to develop a multi-scale analytical framework, and to do that, we leverage a higher dimensional presentation, of a fast dynamic derived from a temporal differentials, and strategically utilize the common eigenvalues of that higher dimension, across temporal scales to predict the flow dynamics in our measurement dimension, or like time dimension. In this discussion, we are going to introduce that framework that we talked about, and we are going to try to see the performance of this framework through a series of case studies over the power system analysis, specifically in a transient state, and see what would be the result of the newly introduced hybrid data-driven network. The challenges, to delve deeper into the challenges, we have to look into the concept that the current analysis are failed to capture the multi-scale spatiotemporal complexities in a system, especially during the transient states, because they inherently rely on a certainty regarding the weak averaging principle and gluing conditions through that multi-scale system or multi-physics system. If we wanted to connect them to the theories that describe these condition of weak averaging principle and gluing condition, we could name that they normally typically assume, or that the system is following the Lipschitz conditions, or the slow dynamics or global dynamics, and they assume the stability criteria that is provided by the Lukhanov theory. These are the foundation of the current methodology. Those current methodology, which we describe it in two categories, one model-based, and the second one is the complex network-based analytics, they normally rely on a deterministic model and only consider the uncertainty in the model as either predictable or bounded, which basically means to analyzing the steady state and transient state, they already assume that those steady state or transient state is already established. The model-based analytics normally rely on a differential equation. On the other hand, the complex network analysis try to represent the system with the incidence matrix, adjacency matrix, and Laplacian matrix, and normally try to quantify the behavior, the dynamical behavior, and the transient stability of the system through analyzing the Laplacian matrix. Now, regarding the nonlinearity introduced to the system, here we describe the nonlinearity in two different categories. One is the module level nonlinearity, or the nonlinearity that we all know. This nonlinearity is a higher order dynamical system divided from the linear terms, introduced by each component within the system. So this nonlinearity is introduced by the component, is tied to a certain component, okay, and propagate through the system and disperse through the system following the same nature, the same physical properties that the linear terms would experience. Now, when we have a multi-scale, multi-physics system, components in our system, the interaction between these components and these dimension scales can generate new dynamical terms. These new dynamical terms are not directly tied to a specific components. Okay, so it's network-based or system-level based generated terms and do not adhere to the typical dispersion characteristics of the system. This type of nonlinearity here, we call it system-level nonlinearity. This system-level nonlinearity introduces a level of unpredictability leading to the multitude of possible outcome and response disturbances, okay, and which basically follows the theory of a chaos theory, chaotic dynamic and chaos theory. Now, the framework that we introduced to address that problem of the system-level nonlinearity and address the curse of heterogeneity is a multi-scale hybrid data-driven framework. But what's the rationale between these frameworks? This framework explains the dynamic interplay between the slow and fast dynamic in a multi-scale dynamic, okay, in the system. We try to get help and inspired by the same concept that is introduced in a coupling of energy levels in a diatomic molecules. The repulsive and interactive forces in a diatomic molecules, okay, is used, that inspiration is used as a rationale to develop this framework. But in more detail, when we want to discuss about the system behavior, we normally define the system, we often conceptualize it as an equivalent complete graph. I want to emphasize the difference between the complete graph and topological graph. What you have and the observation that you have, the measurement that you have is on the topological graph, okay? But we could develop a complete graph equivalent to that topological graph, when in complete graph, all the nodes are connected to each other, okay, in a way that for each specific input, we have the same output as the topological graph would have for that specific input, okay? Now that we develop this complete graph, we could describe all the nodes and decompose all the nodes behaviors in our graph into a source and load boundaries, okay, based on any kind of like flow, like for example, in power system, we have energy flow, you might have data information flow, or any kind of like the flow of the energy or the flow of the data in your system. You could decompose all the nodes into source boundaries and load boundaries. Again, I want to emphasize that all the nodes, regardless of the topological characteristic that they have, okay, would contribute to the load boundaries and source boundaries. Now that we have these two boundaries, if we normalize the nodes, all the characteristics of the system would be inherently analyzable through the interaction of these two boundaries, the source boundaries and the load boundaries, which, inspired by that diatomic molecule, we could analyze the interaction between these two boundaries. Now, to do that, and as we discussed that, we wanted to like leverage the fast dynamic to predict the slow dynamic. To do that, we are integrating a higher dimensional representation by introducing two new dimensions, phi and psi, okay, that is derived from the differential in time, okay, and propose a framework that leverage the eigenvalue, specifically the common eigenvalues, okay, in that fast dynamic representation to capture the interaction and predict the slower dynamics in our measurement dimension. The fast interaction represented by phi and psi captured rapid changes, while the integration of them over the time would result in a slow dynamic representation, which we know that representation as the measurement or our time t dimension analysis, which basically capturing the gradual process of the flow or the transient events. Okay. The generic network-based data-driven analysis normally rely on a certain level of sparse regression methodology. Okay, the network-based aims to identify the system critical components and inherent structure, okay, by tackling the curse of dimensionality. To do that, they normally define the system dynamic as a differential equation. As you could see, like if the system state is defined by v of t, we could describe the function f as the dynamic of system where the dv over dt would be equal to the f of vt. To determine the function f from the available data, a time history of the system state v would be organized. Also, the history of the derivatives of the system would be organized within a matrix form. And then we would use a certain libraries, the certain function of libraries, to describe the relation between the derivatives and the actual states through that function. The sparse regression problem is normally formulated to determine the vector of the coefficients that would activate that libraries, the terms in our function libraries. Okay, that sparse regression normally penalize the errors and the multitude of the elements. So by minimizing the errors and the number of the activated elements in our functional library, in our library of the functions, okay, we basically would end up in a sparse models that could describe with a certain level of acceptable errors, that could describe the relation between the v dot, the differential of the states, and the state, which basically is the function f that we described earlier. But to enhance this and tackle the curse of heterogeneity and deal with the multi-scale nature of that dynamic, we try to develop a hybrid method. Okay, how to do that? We integrate a delay embedding solutions and a stochastic autocovariance analysis in a higher dimensional phase space to address these challenges that is posed by curse of heterogeneity. But how we could actually implement that hybrid method is that we develop first, in the first step, we develop the Hankel matrix of our measurement variable in our time dimension. So the Hankel matrix is the matrix developed by record of the measurement of the states and the delayed versions of that same record of the states. When the Hankel matrix is developed, we run an SVD, a single value decomposition on the matrix, and yield the component decomposition used by single value decomposition. The result of that decomposition would end up analyzing the system, okay, coming up kind of like introducing the eigenvalues of the system in a certain format that distinguished the linear terms and the linearizable nonlinearities, which we call it module level. We called it module level nonlinearities, and distinguishes from the second order or linearizable components of system. And we could describe it as the derivative of our state would be equal to the A times the state plus that second order system level nonlinearity here. Now, A here is the linear dynamics. it's not just linear terms. It describes the linear terms and all the module level nonlinearity that we could linearize through the system. VT is our state of the system. Okay. The matrix B would introduce the eigentime delays coordinates for what we call second order of forcing terms in our model. And VR is actually those nonlinear terms, the second order system level nonlinear terms. Now, based on that description, we basically, what we mean by that last equation that you saw in the previous slide is that we describe the model in a new way of categorization of the data. Okay, before in a current methodology, normally the data is either linear or noise. The harmonics or nonlinearities also have the potential of getting introduced as a function of that linear terms. Okay, but now in this new categorization, we have the linear and linearizable dynamical terms, which basically means the first order dynamics, okay, and the nonlinearities that are either trivial or component level nonlinearity, which basically means we are really could linearize them into the system, into our model. The second category would be the nonlinear dynamical term, which is the second order nonlinearities, the system level nonlinearities. They are non-trivial, okay, and they are not tied to a certain components, and they are in a system level. And the third category would become like the conventional neglected data, like the errors or noise and whatnot. Now that we described our model, let's try to demonstrate the performance of this model over a case studies. For a case studies, we use the IEEE standard 15 bus system. As you could see here, we have the characteristic of our system, and we introduce three scenarios, okay, with a conventional monoscale dynamic, the combination of the monoscale and multi-scale dynamical component, and the purely multi-scale dynamical component. We have several scenarios. In each scenarios, we introduce an abrupt change or fast dynamical change by introducing a fault, and we introduce also a slow change or gradual change into our scenarios by having a low change in our power system. When we use the generic algorithm without that hybrid model, the result shows a satisfactory identification when we talking about the monoscale dynamic, okay, in both steady state and transient state. In transient state, both abrupt and gradual changes, when we talking about the monoscale, the generic network-based data-driven analysis could easily identify the model of the system and follow the model of the system. And when the change happens, very fastly, they could recognize the change and modify the model and follow the new characteristics of the system. When we categorize those components that we find over the analysis of the system, okay, the terms that is active on analysis of the system, when we're dealing with a monoscale system, you could see here that the mostly active terms are the first order terms, which is quite expected because we have monoscale. They are mostly linear or linearizable system, and we already theoretically expected that we have only first order activated, and the second order system level nonlinearity and the errors are nearly zero. Okay. In order to show the effect of the module level nonlinearity, okay, we introduce a higher order conventional system, the 7th order model of our conventional system, okay, which introduce up to 7 order harmonics in a component level into the system, and saw what happened in a generic algorithm to analyze those models. And as you could see, again, the model was able to recognize the system dynamics and have less than a 1% of harmonics or error. When we categorize the active terms, considering the existence of the component level nonlinearity, we still see that the domination of the active terms belongs to the first order, okay? And the second order and third order noise, system level nonlinearity and noise level nonlinearity is merely close to 0 and have a low impact in the dynamic of the system. When we introduce a combination of the multi-scale and mono-scale dynamical components into our system, now the generic model have a problem to accurately identify what's happening in the system. As you could see, the actual data here, you could see the actual data includes gradual system, the sine behavior, this sinusoidal behavior that we see in the graph, and it has a fast interaction, the fast variation, which comes from that multi-scale, fast and slow dynamical components. But the generic model that was supposed to identify the actual model of the system, behavior of the system, was not able to identify the fast interaction, okay? And if you could see, it translate that fast interaction into errors. And you could see here the deviation from the amplitude of the sine waves, okay? And the deviation of the phase difference of the sine waves in each cycle, okay, that you could see in the black graph is basically the errors identified by the generic model, okay, which in reality, those errors were the actually the fast dynamic that the model could not identify. And when we categorize those dynamical terms in those three categories, we could see that now that we introduce a multi-scale component in our system, you could see the importance, the impact of the second order system level dynamics getting higher and start to show itself as actively influencing the dynamic, the general dynamic of the system. So here you could see that the second order system level nonlinearity had a higher impact in compared to the previous scenarios that we didn't have a multi-scale component. In a scenario that we have 100% integration of the multi-scale components, now we could see that, first of all, we know that based on the scenarios that the generic model could not accurately identify the multi-scale. But when we categorize the identified terms, we could see that basically the dominance of the components shifted from the first order to the second order. Now that we have 100% multi-scale dynamical component, it's the system level dynamical term, that second order nonlinearities that are actually governing the system instead of those components that are actually actively are in the system. Okay, here in the blow graph, you could see the trajectory of the dominancy in the active terms in a system. When the blue graph shows the monoscale system, as you could see with the harmonic, with the module level component harmonics, as you could see, the first order components are dominating the dynamic of the system, and there is a certain level of second-order harmonic, second-order nonlinearity, second-order terms, which is basically caused by those propagation of that component level, module level nonlinearity introduced by those components. But compared to that, you could see that when we introduce a multi-scale dynamical term in a black graph, okay, when we introduce a multi-scale components, okay, the shift of the dominancy is toward the second order. Now, the second order dynamic have influence on the overall governing model of the system. And when we talk about the purely multi-scale dynamical components in our system, you could easily see in a red graph that actually the second order, the system level terms in our model is completely dominating the system and have more influence than the first order terms that we have in our model. Now, the higher order, to summarize the result, we could say that the higher terms reveals a more intricate system response characterized by a broader spectrum of the frequency and richer harmonic content. Okay, the higher order terms signify the departure from the conventional understanding that consider the dominancy of the first order terms. Okay. In addition to that, system non-diagonal eigenvalues become a crucial indicators in system behavior. Okay. And the dominance of the higher order terms indicate more pronounced system level nonlinearity. Therefore, the eigenvalues linked to those higher order dynamics play more critical role to determining the system stability. So now, when we want to analyze the system stability, we cannot only rely on the first order models, okay, and the linear models, because when we have a multi-scale component in our system, now these higher dynamics are actually the terms that determine the system stability. Now, when we introduce that multi-scale hybrid data-driven framework, we saw that this newly introduced multi-scale data-driven framework could actually predict accurately both slow dynamics and fast dynamics. Again, both in a steady state and transient state. You could see that there is a very neglectable error between the hybrid approximation and actual data in a steady state, as well as the transient state. Okay, you could see that very fastly our hybrid method modified the model and could follow the change in the system in a transient situations. And when we aggregate those fast dynamical terms, okay, we could actually have a prediction of a slow dynamics that could predict and could detect all the changes that happen in our scenarios. If you remember, in our scenarios, we introduced a fault as an abrupt change, and you could see the aggregated result of our fast dynamical analysis was able to detect the happening and the clearance of the fault in our system, which is the abrupt change, and also could detect the gradual load changes that we have as a slow transient changes in our system. And they could easily detect or predict those transient events. Now, illustrating by these compelling case studies, we introduced the challenge posed by curse of dimensionality and heterogeneity in the complex multi-scale interactive dynamics. We explained the essentiality of having hybrid data analytics when we're dealing with a multi-scale stochastic autocovariance analysis. Okay, and we show the inadequacy of a conventional network-based data-driven system. Again, when we're dealing with a multi-scale system, especially in a transient event, we proposed our multi-scale hybrid data-driven analytics using delay embedding and stochastic autocovariance analysis for modeling those CUP multi-scale dynamical system. We categorized in this study the nonlinear dynamics into newly introduced categories, the first order terms, which include linear terms and linearizable terms, i.e. we mean the module level or component level nonlinearities, also described in that first category. The second category would be the second order terms, or as we call it, the system level nonlinearity, okay, which are not linearizable through the system. And the third order would be the conventional noise and errors that are normally negligible in our analysis. And the result of our case study shows that the fundamental shift is happening in the system dynamic, revealing system level nonlinearity compared to the module level nonlinearity, and the dominance of the system level dynamics compared to the component level dynamics. But what would be the outcome of this study? This introduced framework, first of all, as we see in the result, enables a more precise assessment of our system stability. It could help identify optimal operation point and maximize the efficiency and resiliency when we have multi-scale component in our system. It could ensure operational decisions based on the current network configuration of the data. It could analyze the shift from the static data derived from the models and the dynamic data obtained through the direct measurement. So using this hybrid model, we actually could go toward more accurate and more trustable real-time dynamic analysis. And we could refine a real-time estimation of the system behavior, as you saw in our result, based on our fast dynamical system, and predict and evaluate the slow dynamical system purely by analyzing the fast dynamics. Thank you for your attention. I would be happy to answer any question or concern regarding our system. You could contact me via email as reza.candizi@ou.edu. You could have access to more detailed description of what we discussed, the framework that we introduced, and the studies that we conducted over that framework through our recent publications that is available on my personal webpage and my LinkedIn webpage. Thank you for your attention. Have a good day.